In this video, we'll learn how to draw shapes using simple equations. It doesn't seem like much, but since we'll also learn how to cut, transform and move these curves, your drawings will be limited only by your imagination. And if you want, you can even animate them. This video can be interesting for art lovers of all kinds, for the simply curious, and especially for students working on function studies. In fact, understanding graph transformations is a great way to get an idea of the graph of a given equation, or vice versa, to figure out the equation from a graph. Ready? Let's get started. Translating geometric figures into equations has proven to be an extraordinary tool for centuries of mathematics, and this still has many applications today. For example, it made it possible to move from pixel-based images to SVG images, which don't lose quality when scaled up precisely because they are saved as equations. This also helps reduce file size. In fact, the equation of a curve, on its own, already contains all the information about the curve. Even if someone had never seen the drawing before, they could recreate the curve just from the equation. In a way, that equation is the curve's genetic code. But how can a geometric, visible object like a curve hide something as abstract as an equation? The connection is provided by the Cartesian plane. It's the very bridge we are looking for between geometry and algebra. By introducing a Cartesian reference system on a plane, each point can be identified by its coordinates, that is, by a pair of numbers. The first value, usually labeled x, indicates the position along the horizontal axis, while the second value, y, indicates the position along the vertical axis. So, if we take an equation in x and y, let's start with something very simple like y equals x. How does this represent a set of points on the plane? We just need to interpret the equation as a condition. We'll select only and only the points on the plane whose x and y coordinates satisfy y equals x. Which points are these? 1, 1, 2, 2, 3, 3, and so on. But you can also choose non-integer or negative numbers, as long as the pair is made up of two equal numbers. In short, the points identified by the equation y equals x are the points on this line, known as the bisector of the first and third quadrants. To show you an example of a curve that actually curves, let's see which points on the plane have coordinates that satisfy x squared plus y squared equals 1. This condition is satisfied by all and only the points whose distance from the origin is equal to 1, and for this reason it forms the unit circle. To draw curves, we'll use the software Desmos, where you can freely create equations in x and y to see the corresponding curve come to life. You can also use equations in polar coordinates r and theta, where r represents the distance from the origin and theta the angle relative to the positive semi-axis x. However, to draw well, you don't need to know the equations of many curves. Just with lines and circles, by learning how to modify their equations to cut, rotate, scale, and translate them, you can already achieve great results. I had fun recreating Homer and the channel's logo. Enough chit-chat, now I'll teach you how to do it. Let's access Desmos, the famous free graphing calculator that also lets you save your work and explore a large gallery of shared projects. The images you've seen so far were actually created with Desmos. In the software, you enter equations in the left column, and you'll see the corresponding curves appear on the Cartesian plane to the right. The settings allow you to manage the display, but to zoom in or out, you can use the mouse wheel or pinch with two fingers if you are on a touch device. For our first drawing, I thought we could work together to derive the equation for drawing a heart. How do we proceed? Whenever you want to draw something, Since it's very difficult to guess the final equation right away, it's definitely more convenient to try to achieve that result starting from a simpler figure by applying appropriate transformations. What these transformations are and how they affect the equation of the drawings will be explained in this very video, but not just yet. So don't worry if it's not immediately clear how to get the equation for the heart. What's important now is to understand that such transformations exist, even if they might not be intuitive. The heart, for example, already has symmetry, and this is a good thing, because if we find the equation for half of the heart, there is a transformation that can mirror it, so it will be enough to find the equation for half of the heart. What remains is a piece of a curve similar to a flattened circle, called an ellipse. You just need to complete it like this, see? Now let's rotate the shape slightly clockwise. Squish it from the sides, and here is a circle, whose equation we already know. We'll derive the equation of the heart starting from the unit circle x squared plus y squared equals 1 and retracing the transformation used. The first thing to do is to stretch the figure horizontally. This is one of the transformations we'll see. It's called dilation. To apply it, you simply replace every x in the equation with x divided by the scaling factor. To double the horizontal size, we replace x with x divided by 2. Now, to continue retracing the steps toward the heart, it's time to rotate it 45 degrees counterclockwise. Rotations are also valid transformations. By replacing every x with x plus y and every y with minus x plus y, you effectively perform a 45 degrees rotation, although with a slight shrinking effect. Transformations always work like this. You replace the variables in the previous equation with new expressions. There is still one step left, keeping only half of this shape, the right side, and reflecting it over the y-axis to get the heart. This transformation is very simple. You replace every x with the absolute value of x. Here is the heart. The final equation can also be simplified a bit with some algebra, becoming 5x squared plus 5y squared equals 6 times absolute value of x times y plus 4. If you replace the equal sign with less than or equal to, you will also get the interior points, and you can use Desmos to fill in the shape with color. In this first drawing, we used 3 transformations to go from the circle to the heart. The more transformations you know, the easier it will be to create complex drawings. So, I'll quickly show you the fundamental transformations. We'll see how to reflect the image across the Cartesian axis, how to rotate it by 90 degrees, how to stretch or compress it, and finally, how to translate it around the plane. We'll also look at how to cut out or combine multiple curves. For all the other transformations that might be useful but that we won't cover in this video, I'm leaving a chart linked in the description. Besides showing many other useful transformations, the chart provides equations for other basic shapes beyond the lines and circles, like polygons, stars, flowers, as well as the equations of the main function graphs studied from the high school onward. That said, let's start exploring these transformations. If you have the equation of a curve in variables x and y and want to reflect it over the y-axis, you just need to apply an axial symmetry by replacing every x in the equation with minus x. In fact, the only difference between 2 points mirrored across the y-axis is the sign of the first coordinate. Similarly, to reflect the figure over the x-axis, simply replace y with minus y. Nothing more to say. If you want to rotate your figure 90 degrees clockwise, you need to replace, simultaneously, x with minus y and y with x. In fact, swapping x and y reflects the graph across the bisector of the first and third quadrants. And the minus sign in front of y produces an additional reflections over the x-axis. the combined effect of these two reflections is precisely a 90 degrees clockwise rotation. In the chart linked in the description, you'll find the formula to rotate the figure by any angle you like. But to fully understand that formula, I need to talk you about rotation matrices, and I plan to dedicate a separate video for matrices. So, let's move on to dilations, which we've already encountered earlier. If you want to stretch or compress the figure, you can replace x with x divided by k, or y with y divided by k, depending on whether you want to do it horizontally or vertically. For values of k greater than 1, you get a dilation. For values between 0 and 1, a compression. You can use both these transformations to enlarge or shrink a figure. For example, halving both x and y doubles the size of the figure. As for translations, I suggest applying them as the last transformation. First, focus on adjusting the size and orientation of the figure. Once the figure is ready, replace x with x minus a and y with y minus b to move the figure a units to the right and b units up. To move the figure to the left or down, use x plus a and y plus b respectively. At this point, before explaining how to cut out and combine multiple curves, I'd like to show you how the previous transformations allow you to quickly derive the equation of a curve given its graph. A very useful skill for high school students. Let's take the graph of this parabola. What is its equation? We start from the standard parabola with the equation y equals x squared. Notice that, compared to the standard parabola, the one given is flipped upside down, so we apply a reflection over the x-axis by replacing y with minus y. Before translating it, observe that our current parabola is much narrower than the given one, so we apply a horizontal dilation. As you can see from the scale on the axis, the given parabola is 3 times wider, so we replace x with x divided by 3. Now the parabolas seem to overlap. Indeed, we only need to perform a translation. Comparing the vertex positions, we see that we need to move 2 units to the right and 1 unit up. So we replace x with x minus 2 and y with y minus 1. And voila, we get the final equation. If you want, you can simplify it with a few algebraic steps to put the equation into standard form, but the exercise itself is finished. Closing this practical example for students, let's get back to the transformations useful for drawing and learn how to use scissors and glue. Let's take a curve whose equation you know. Unless you bring all terms to one side, we can assume that the equation is of the form function f in variables x and y equals 0. If we want to keep only part of this figure, say the portion where x is between values a and b, we can use this new equation, which I won't even bother reading aloud. Although it mathematically does its job, it doesn't look nice. Moreover, Desmos also struggles to handle formulas like this. Fortunately, there is a command to crop figures. On Desmos, you just need to add, at the end of the equation and inside the curly braces, the area of the graph you want to keep. For example, minus 1 less than x less than 2 will keep only the part of the graph between x equal minus 1 and x equal 2. You can add more conditions simply by including them inside the curly braces. For example, adding y greater than 0 removes the part of the graph where y is negative, keeping only the portion above the x-axis. This command is definitely much better than the previous equation. If two figures have equations f1 and f2 equals 0, by the zero product property, the new equation, obtained by their product equals to 0, represents both figures at once. However, it's not necessary to include the entire drawing in a single equation. Although I admit it was mathematically satisfying to derive the equation that generates Homer. Desmos actually allows you to plot multiple equations simultaneously. By clicking on the circle next to each equation, you can choose to hide or show the associated curve. At this point, all that's left is to invite you to experiment with mathematical drawing. Remember to check out the chart in the description to have access to more basic figures and transformations to refine your creations and your studies. I also encourage you to try drawing curves in polar coordinates using equations of the type r as a function of theta, which can be very rewarding as well as parametric curves. If you want to animate your drawings, you can add parameters, meaning additional variables within the equation, allowing the software to assign values to that parameter from a customizable range. This will continuously change the graphical output, creating the animation. Another possible development is moving on to 3D graphics. There's always plenty left to discover. The important thing is to keep going and not be afraid. See you in the next video. Meanwhile, don't panic.